Okay, in this video, we will discuss strategies for determining whether a hyperreal number is infinitesimal, finite but not infinitesimal, or actually infinite. This is a really important um, technique, especially when we get into defining the standard part function in the next section. So definitely spend some time with this, practice this, do lots of problems. The textbook has tons of problems you can work on because being able to conduct this analysis on a hyperreal number is very important. So first things first, let's get our definition up there. So we will say that a hyperreal number x is an infinitesimal if it is bigger than every positive real number and smaller than every, sorry, I had that backwards, smaller than every positive real number, but bigger than every negative real number. That's what's being said right there in that inequality, that x, take any real number you like, and x will be smaller than it, and obviously bigger than its negative version. We're going to, for the whole set of infinitesimals, we'll use this symbol here, the double scripted E. So get used to seeing that. I'll use that in my examples here. We'll use it in our conversations in class. We'll also use this symbol on exams. So this is not a symbol that's in the textbook, but it's one that I use. Now, if we have an infinitesimal, we'll say it's negative if it's less than 0. That's what we would expect. And then it's a negative infinitesimal. If, on the other hand, it's bigger than 0, we'll say it's a positive infinitesimal. So let's say we don't have an infinitesimal, then the other category we could be in is finite, but not infinitesimal. So we have a finite number if it's between any two real numbers. So if I can find a real number a and a real number c, so that x is bound between them, so it's less than c but bigger than a. If the number is in between two real numbers, then it can't be infinitesimal. Right? It doesn't satisfy this definition because it's bigger. It's bigger than some number a. But we'll see it's not infinite though because it has a real number that's less than. So we'll just say it's finite and stress the fact that it's not infinitesimal. Now, on the other hand, if we don't have an infinitesimal, we don't have a finite number, then our hyperreal is going to be an infinite number. And either it's going to be positive infinite, which means that it's going to be bigger than every real number a, or it's going to be negative infinite, meaning that it's smaller than every real number a. And whether it's positive or negative will denote the set of all infinite numbers with the double script m. So these are our three categories. We have infinitesimals, finite but not infinitesimal, and then infinite numbers. These three kind of big categories, and then the infinitesimals can be subdivided into positive and negative infinitesimals. I guess finite numbers as well can be positive and negative numbers, and then infinite numbers can also be positive or negative. So those are our definitions, but now we need to have some kind of strategy for determining whether a number is infinitesimal, finite, or infinite. So this is straight from the book. These are going to be our rules. They should make sense, and I'll try to give some explanations for why these things should be true. So if we've got two infinitesimal numbers, we'll look at epsilon and delta. We have b and c are hyperreal numbers, and then h and k are infinite hyperreal numbers. Then we have here that 0 is the only real infinitesimal. Every real number is finite. If epsilon's an infinitesimal, and so it's negative, it'll be a negative infinitesimal. So looking at these rules here, the negatives, that if you've got an infinitesimal, it's negative as an infinitesimal. If it's finite, it's negative as finite. If it's infinite, it's negative infinite. That should hopefully be pretty straightforward. Now, regarding reciprocals, Here we have that if, again, epsilon is not 0, so we can actually divide by it, then its reciprocal is going to be infinite. And this should make sense, because if epsilon, say, is less than a for all a, then remember our rule for, and I should probably use a different color here, yellow is hard to see, then if epsilon is less than a, then its reciprocal, remember that we'll have 1 over a is less than 1 over epsilon. Now this was true for every a, so now this is saying for every real number, because I can think of every real number as a reciprocal of something, then 1 over epsilon is bigger than it. And that's definitely our definition of an infinite number. So reciprocals of infinitesimals are going to be infinite numbers. Same going for if I have an infinite number, its reciprocal will then be an infinitesimal. And then finally, finite numbers, their reciprocals are still finite. If I, so looking at sums, if I add two infinitesimal numbers, then it's still infinitesimal. If I, so right here, if I add infinitesimals, I still get infinitesimal. If I add a finite to an infinitesimal, well, it still stays finite. It doesn't become an infinitesimal. Similarly, if I add two finite numbers, I'll still be finite. Now, here's going to be really important. It's quite possible that by adding two finite numbers, I end up with an infinitesimal. So an example would be, say I have 3 plus an infinitesimal, and then I'm adding maybe, I don't know, negative 3 plus some other infinitesimal, then this would be equal to epsilon plus delta, which from adding two infinitesimals is an infinitesimal. So this would be an infinitesimal, even though the two things that I added together were not. This is finite, but not infinitesimal. But when I add them together, right, the real parts kind of canceled out, or what we'll call the standard parts canceled out, and we got left behind is just an infinitesimal. So it's quite possible that I add two finite numbers and end up with an infinitesimal. Finally, with sums, if I add an infinite number and an infinitesimal, if I add an infinite number and a finite number, I stay infinite. Right? Really big plus something small is still really big. In terms of products, well, if I multiply two infinitesimals, or if I multiply an infinitesimal and a finite number, either case I get an infinitesimal. If I multiply two finite numbers, then it will still stay finite. It can't become, in this case, it cannot become infinitesimal. And if I multiply a finite number with an infinite number, or if I multiply two infinite numbers, I will still be infinite. Quotients, I find students find quotients the most difficult to work with and just kind of get a handle on. But if I have epsilon divided, an infinitesimal divided by a finite number, or an infinitesimal divided by an infinite number, or a finite number divided by an infinite number, either three cases, this is an infinitesimal. And my recommendation to students is actually don't think of this as a fraction, but think of it as a product. So, for example, epsilon over b is the same as 1 over b, which is a finite number, times an infinitesimal. Now we're in the first case of a product. If I take a finite number and multiply with an infinitesimal, I get an infinitesimal. So that's why epsilon, or an infinitesimal divided by a finite number, is still an infinitesimal. Similarly, if I take an infinitesimal and divide it by an infinite number, well, this is the same as 1 over h times epsilon. Now, 1 over h, as we know from our reciprocals, is an infinitesimal. And epsilon's an infinitesimal. And so this whole product, again, by the product rule, is an infinitesimal. And then finally, b over h we can think of as 1 over h times b, and again, infinitesimal, finite, by our product rule is infinitesimal. So I recommend to students, again, the quotient laws here oftentimes are a little bit difficult to reason through, but if you rewrite it, and it's good practice of your algebra, if you rewrite it as a product of two numbers, then oftentimes it's easy. So we have, so this is our list of quotients that become infinitesimals. If B and C are finite numbers, but not infinitesimals, when I take the quotient, it's still a finite number. And then this is just the kind of flipping all these on their heads. So if an infinitesimal divided by finite is infinitesimal, then its reciprocal, b over epsilon, would be infinite. If epsilon over h is infinitesimal, then its reciprocal, h over epsilon, is infinite. And if b over h is infinitesimal, its reciprocal, h over b, is going to be infinite. All provided, of course, that epsilon isn't 0, in which case we couldn't actually even do the quotient. And finally, looking at roots, if I've got an infinitesimal number that's positive, then I could take any root and it stays an infinitesimal. It still stays small. If, on the other hand, b is finite and I take any root, it'll stay finite. And if h is a positive infinite number, I can still take a root of it and it would still be infinite. Now, there's 4 cases that we didn't look at. And these 4 here, if I'm looking at the time, I recognize we're long. So I will pause now, and in the next video, we'll address these indeterminate